I'd like to continue our discussion of volcanic activity. I think before I do, I better tell you what a volcano is. I guess we haven't gotten around to defining one yet. By definition, a volcano is the conical structure that builds around a vent. Vent, of course, being the hole in the ground through which all this stuff comes. So the conical structure that builds around a vent is a volcano. Note, in that definition, there's no indication of size. Now, this is one of the things you'll find if you take a course in geology, that geologists rarely concern themselves with the size of things. We're more interested in how they got that way, the mechanism by which they got that way. Size is totally immaterial. For example, you can have a volcano that technically could straddle with your legs. As long as it was formed by volcanic means, it would be a volcano. Obviously, most of them are a little bit bigger than that. But anyway, that's what a volcano is. Now, in terms of kind, I think there are three fundamentally different kinds of volcanoes. The first one, and the simplest, of course, is the one we've referred to, the so-called cinder cone. Now, cinder cones are primarily the result of basaltic eruptions. Now, picture, for example, a basaltic eruption. Remember, very little gas now. And at the most, you're talking about an amount of gas that may throw the molten rock up into the air, maybe 1,000 feet, 2,000 feet at the most. And as the molten rock goes up, it sort of spreads out and breaks into little fragments, which solidify on the way down, and fall around the vent and form a cone. And the size of the materials are cinder size, so we call it a cinder cone. Now, the cinder cones are very, very characteristic of any region that is undergoing basaltic eruption. For example, if you went to the Rio Grande Rift in Arizona or in New Mexico and up into Colorado, you'd find cinder cones all over the place. They're very, very common. You went to the island of Hawaii, there are very nice examples of cinder cones. So any place you have a basaltic scenario, you're going to have these cinder cones. Now, they usually don't get very big, mainly because there's very little energy to throw them much over 2,000 feet, so that probably would be about as high as you'd ever expect to see one. And since they're just sort of loose oftentimes, they're eroded away pretty fast too. So anyway, but that would be a cinder cone. Now the other two are the big guys. And the first one I want to talk about is a thing called a shield volcano. And this allows me to go back now and pick up our little discussion of the hot spots. So what I want you to do is to picture a hot spot, as most of them are, underneath the ocean basin. What's going to happen is from the hot spot, now remember that's the blob of basaltic magma that forms right at the very top of the asthenosphere. What happens is then it breaks through into the lithosphere, so we're talking now oceanic lithosphere, and forms another magma chamber, which you might ask, why would it do that? And I'm not sure I know the answer. It's just that all of our information seems to be that there is another magma chamber formed within the lithosphere. And then it breaks through to the surface. Now we're talking about the surface of the ocean bottom, so picture now an eruption of basaltic lava on the ocean bottom, not building up very high because it's very, very fluid, so it spreads out, and we put down one layer, and then the next eruption does the same thing, another layer that spreads out. And as we build a cone, but note the cone now is not very high relative to its width. In other words, much wider than it is high. And the reason why is because you can't stack liquids up any higher than that. For example, if you took pancake batter and poured it on a griddle, just picture that. It heaps up in the middle and flows out to the side. So this would be sort of like a gigantic pancake in a way, but I guess that's not a very scientific term to use. So back in the days when they named this, I think somebody thought it really looked like the shield the old warriors used to carry, so they called this a shield volcano. So that's what develops over these hot spots. Most of them, again, on the ocean bottom. So if you went to the ocean bottom, there would be an R, who knows how many thousands of these things down there, each of them forming over a hot spot. Remember, these hot spots, we don't really understand them, but one of the things we do know, they come into being, they last for a while and die. Apparently, most of them probably don't last very long, so they may last long enough to make their individual little shield volcano. Many of them never make it to the surface, and if they don't, then we call them seamounts. So a seamount basically is a shield volcano that builds from the ocean floor and doesn't reach the surface. And if you look at maps of the ocean bottom, there are literally hundreds and hundreds and maybe thousands of these things. Now, if it does break through to the surface, then of course we're talking about a volcanic island. And the best example I can think of that you would remember would be the Hawaiian Islands. Each of the Hawaiian Islands is in fact a shield volcano that built up above the surface. And we're going to talk about the Hawaiian Islands in another lecture, so I don't want to get into those too far. We want to spend some time talking about them. But anyway, that would be the shield volcano. Most of the shield volcanoes are on the ocean bottom. There are shield volcanoes, for example, on land. They're not as common, not as numerous, but for example, just south of Bend, Oregon, there's a place called Newberry Crater, they call it. Well, it's a shield volcano. So you do have these things on land, but my experience of going to volcanic regions, most of these shield volcanoes do indeed build on the ocean floor. Okay, so that would be the shield volcano. Now on to the stratovolcano. Now the stratovolcano is the kind of volcano that's going to be associated now with the zones of subduction. We're talking here arc volcanoes, either the continental arc or the island arc. We're talking about volcanoes that are built out of andesitic magmas erupting to the surface. Now remember, these are always explosive. So here's the way it works. Picture a brand new stratovolcano or composite volcano about to be constructed. The first eruption is going to be an explosive eruption, lots of pyroclastic material being created, bits and pieces of rock, blocks, bombs, the cinders, the whole bit, and it's going to accumulate around the vent. Now here's the important thing. If you think about the pile of debris around the vent, there's a certain angle that stuff makes, and it's called the angle of repose. Now here's an interesting point. Excuse me, it doesn't make any difference what the material is or what the size is, as long as it's solid, of odd shape, and you pour it into a pile, the pile will have just about that same angle of repose. It's about 40 degrees. And I don't care whether you're potting up pyroclastic material around a vent or whether you're pouring salt out of a container, it will form that cone, and that angle of 40 degrees will be pretty much reproduced every time. It doesn't make any difference the size of the stuff. That's called the angle of repose. So here we have then a cone now that has an angle of repose of about 40 degrees, and then following the eruption, then the andesitic magma comes out. Now it's becoming lava. It flows down the sides of the cone, covers the cone, seals it off, and that's eruption number one. And then every one it does after that, explosive eruption, pyroclastic material, volcanic eruption of the lava, andesitic lava is flowing down and seals the pyroclastic stuff. So note, every time that occurs, what you're dealing with is a composite. The composite refers to the fact that it's a composite of two different materials, pyroclastic stuff and the andesitic lavas, and the strato refers to the layering that's building. And note, it builds very high, very fast relative to the width. And as a result, you have the classic conical structure that most people think about when they think about volcanoes. The best example I can think of would be, of course, Mount Fuji. Mount Fuji is probably one of the most beautiful, in many people's eyes, of volcanoes in the world. It is a perfect cone. Well, I might just throw out that before Mount St. Helens blew 1,000 foot off her top, she was oftentimes referred to as the Mount Fuji of North America, because that also was a perfect cone until the eruption of back about 1980. So anyway, if you look at all of the volcanoes within the island arc or within the continental arc systems, each one will be basically a strato or a composite volcano. So that's the ones you see. All right, so much for the kinds of volcanoes. Now let's get back to talking about the eruptive styles. We talked about why some volcanoes erupt violently and others don't. It's simply a question of the amount of gas involved. The more gas you've got, the more the erupting style is going to be more explosive. What the volcanologists have done, they sort of pigeonholed volcanic eruptions into various kinds of what they call phases. The first phase is called the Hawaiian Phase. Now, the Hawaiian Phase is described as nothing but the quiet evolution of lava. The name obviously comes from the eruptions on the big island of Hawaii. And again, if you go there, that's what you will see. You'll see the eruptions of of basaltic magmas coming to the surface and becoming lavas. You'll find maybe a fire fountain, things like that, but you'll find no explosions. It's simply nothing more than the quiet evolution of lava. Any kind of a basaltic eruption at all anywhere in the world will be of the Hawaiian phase. I don't care whether it's on the Hawaiian Islands or on Iceland or on an oceanic ridge. Wherever it is, it's the Hawaiian phase. It's simply nothing but the quiet evolution of lava. The implication is that you can go there and you can get as close to the erupting site as you want, and you don't have to worry about being blown away by some big explosion because they just don't have them. The only time I can think of where you would have any kind of an explosion associated with a basaltic eruption, and this has happened a few times in the Hawaiian Islands and on the Iceland, but it's been where the magma on the way up is run into water. For example, on the Hawaiian Islands, perhaps it runs into groundwater. And of course, the groundwater then flashes to steam, and you have a phreatic explosion. But you see, that has nothing to do with the magma. That has to do with generation of gases that had nothing to do with the original magma itself. So that would be an explosion of sorts. They've had a few of those, but still, I don't think anyone has ever been killed in one of those. And on Iceland, of course, you've seen eruption up there and the big explosion. Well, that's when the magma hits seawater. So anytime you have that kind of a scenario, you may have an explosion. But again, it has nothing to do with the magma itself. Okay, on to the Strombolians. The Strombolian is sort of a step up now in our phase of activity. The Strombolian phase is defined as frequent but mild explosions. Frequent but mild explosions. And it's named after a particular volcano by the name of Stromboli. Actually, it's an island. The island of Stromboli is located just north of Sicily in the Mediterranean, and that's basically its eruption style. About every 20 minutes, it has an eruption. Now, the idea is that if it erupts every 20 minutes, you never have the opportunity to build up much gas. You see, you relieve it every 20 minutes, so you don't have a really big explosion. The explosion is big enough, I might add, to throw some molten rock out of the crater, rolling a little blobs down the sides of the cone, but there's no big explosions. That's the characteristic of it. So every 20 minutes, and this has been going on apparently forever. As a matter of fact, one of the common names for Stromboli, they refer to it as the lighthouse of the Mediterranean. And that goes way, way, way back to the days of the early mariners. And the idea was that during the day they could see it because there was always a plume hanging above the volcano, because obviously it was active, and they could see that plume for many, many miles beyond the normal curvature of the Earth, which is roughly, 20 miles at sea. And then during the night they could still see it because the molten rock down in the crater was actually illuminating the bottom of the clouds. So not only was it visible at day, it was also visible at night. So they referred to it as the lighthouse of the Mediterranean. Now, here's the interesting thing I find in trying to explain that. This is supposed to be now a zone of subduction. This is supposed to be andesitic magmas, and basically it is. But why is it you don't have that concentration of gas? The best explanation I could ever read about it is that there seems to be a possibility that down in the zone of subduction, you also have basaltic magmas being generated. I think everybody agrees on that one. So the idea is that if somehow some of that low viscosity basaltic magma could in fact mix in with some of that higher viscosity andesitic magma, then you've got something sort of in between the two, you see. So then when it erupts, it's going to be sort of in between an explosive type and a non-explosive type. In this case, it's explosive, but, you know, unless you're really dumb, it's not going to kill anybody down there in that crater. So that would be the so-called Strombolian. Not many of those things get reported in the paper because you'd have to report them every 20 minutes, I guess. The Volcanion Phase, that's the next step up now. This is the one you probably hear about. This is the one that is reported in the daily news and on the TV at night. This would be the eruption of Mount St. Helens. Definitely was one of these. And by definition, what Volcanion is infrequent, not very often, but severe. How infrequent? It might be hundreds of years between eruptions. Who knows? But it's not a frequent thing, but it's violent. This would be a very classic eruption of andesitic magmas. This would be a very typical eruption of an arc volcano, the Volcanion Phase. The interesting thing about the Volcanion phase is that it's named after a volcano by the name of Volcano. And there is a volcano, and actually it is an island, also just north of Sicily, and as the crow flies, is something like 50 miles from Stromboli. Now again, think about that. Here you have two volcanoes, literally side by side, obviously associated with same zone of subduction, but equally obviously having different plumbing. There's got to be something different down below that provides one with a fairly low viscosity lava to the surface, the Strombolian, and here a typical andesitic eruption, the volcano. So that's an interesting thing, that the plumbing down below always isn't very clear cut. So anyway, that Volcanion, that would probably be the one that you're going to hear about the most. Now we get to the two biggies. The Pelean. In both the Pelean and the Plinian, what I want you to do is just visualize the most violent thing that you can imagine. So there is really no comparison other than that. But the Pelean, I want to talk about it because this was a very special eruption. This was a particular eruption of a volcano by the name of Mont Pele. Mont Pele is on the island of Martinique in the French West Indies. And if you look at your map of plates, there's a little Caribbean plate, and there's a zone of subduction that curves down around that series of islands and ends down in South America from Cuba, going down around. And that's the little zone of subduction. That's where Martinique is. Mont Pele had always been known as an active volcano, and from everything we could tell, probably erupted in the Volcanion phase. And this particular phase that we're thinking about here, it actually erupted in 1902, as I remember the date. And right from the start, there was something different going on. Right from the very start, the intensity of the eruptions was greater than anybody had expected or had recorded before. More explosions, bigger explosions, more stuff being thrown out. Everything seemed to be very, very different. And it scared a lot of the people on the island, of course. So as the story goes, everybody who lived on the island was wanting to get off the island obviously for protect themselves. And they all moved into a little town, the only town on the island, by the name of St. Pierre. Now, St. Pierre, on an average run-of-the-mill day, probably had a population of maybe 5,000 or 6,000 people. Literally overnight, this plague grew with everybody on the island, so it's estimated that at the time of this event, the population in St. Pierre probably was pushing maybe 30,000 people. Now, what happened on this particular day was described by a ship's captain who was sailing into the harbor, or getting ready to sail. This would have been 1902 now, so he was under sail. And he saw something going on, and I think he said, "I think I'm going to wait." And what he described was the final eruption of Mont Pele. He described, for example, that it was in these enormous eruptions, one right after the other. He said it was like, in his log, like hundreds of cannons going off, one right after the other, right after the other. And then he said the end came. There was this gigantic eruption, and all of a sudden there was this glowing mass that completely enclosed the summit of Mont Pele, and it roared down the mountainside, completely enveloped the entire town of St. Pierre, out into the harbor, setting ships on fire, sinking ships. Even this guy, who was not even in the harbor yet, he was pelted with molten rocks and stuff from the shore, set his ship on fire, and before he could set sail and get out, apparently he lost about half of his men. But anyway, completely destroyed the town of St. Pierre. Everyone was killed, with the exception of two. Now, one of them, and I don't remember the names, unfortunately, but one of them was described as one of those kind of people who would survive any disaster. So he just sort of walked away from it. The other one, this is the interesting one, the other one was spared because he was everything bad in a human being. He was a liar and a cheat and a thief and a murderer. He had actually been convicted of murder and was waiting to be hung on that day. And of course, he was down in the dungeon under City Hall. And when this thing went by, it just took City Hall away. And here's this poor guy down in the dungeon. And then after somebody came in and they started looking around to see what was going on, they heard him hollowing down there, I guess. Went down and dug him out, a little singed around the edges. But you know what they did? They didn't take him out and hang him. They pardoned him I guess they figured he was not really supposed to go on that day. So they pardoned this guy, and the story goes, and I guess this is true, he spent the rest of his life touring with the Barnum and Bailey Circus as the guy who defied Pele, goddess of fire. So anyway, there's a little moral to that story, I guess. But anyway, what happened? What was it really happened there? What really happened was described by the first geologist who came in. He was a Frenchman. And so what he sort of put together, apparently what happened at the very end, probably the entire, if not most of the magma chamber just disgorged all at one gigantic eruption. And so here's this incredible mass of molten rock, superheated steam, pyroclastic stuff. There's so much stuff that it couldn't even blow it into the air. And it just hung there momentarily around the top of this thing in a glowing cloud. And he called it Nuit Ardentaise, which is in French, I think my poor French, of course, is glowing cloud. And anyway, that's what roared down the mountainside and destroyed St. Pierre. Now, we've seen the results of these before. Now that we've seen it, and has had it described, now we can go out and see other places where there is volcanic debris that we now recognize as one of these glowing clouds. So that would have been the so-called Pelean eruption and the Pelean phase. Now, the only difference between it and the Plinian obviously is named after Pliny the Younger, or maybe the Elder, I don't know which. But the Plinian, the only difference between the Plinian and the Pelean is in the Plinian, there is enough force to throw all that stuff up into the air, and so you get this towering column, perhaps 30, 40,000 feet high, of all that debris. The intensity is just the same, it's just that it doesn't sort of hang out around the crest and collapse on itself. So the most violent eruptions you can imagine here on Earth would probably be in one of those two. For example, Pinatubo, when Pinatubo went up in the Philippine Islands, it probably was one of those two. We could argue about which one it was, whether it was Pelean or Plinian, but it certainly was one of those two. It was one of the big ones. The Krakatoa eruption, the Tambora eruption that we just talked about that put the Northern Hemisphere into a dark time, a dark cold time. That had to be at least one of those last two. So anyway, those are the eruption styles. And there is one other eruption style that we haven't named yet, but it's just the most monstrous thing we can imagine, but I'm going to hold that until another lecture. I got to keep you coming back, you see, is the whole idea behind that one. Now, the other couple of things I want to talk about. There are two volcanic features, crater and caldera, that are sort of, a lot of people use them interchangeably, or if they don't do that, they mix them up. And I want to make sure you understand the difference between a crater and a caldera. A crater is simply the opening at the mouth of the volcano. It's at the summit. It's where everything blows out. So every volcano now has a crater. So that's what a crater is. It's simply the opening at the summit of any volcano. Now, the caldera, to show you what it is, let me describe one in formation. Let's see. Up until 7,000 years ago, there was a volcano at the bottom end of the Cascade Mountains, just in the southern part of Oregon, called Mount Mazama. It was a typical stratovolcano, and in the year about 7,000 years ago, and remember now, 7,000 years ago, there were Native Americans living there. This thing went into a violent eruption. It had to be, again, of a Pelean or a Plinian style, because what happened was that a good part, or perhaps all of the magma chamber was disgorged. Now, I suspect this thing probably maybe would have been Plinian, because there's plenty of debris for miles and miles around from this thing. But here's the important point. If you picture a cone, a volcanic cone, and the magma chamber below filled with magma, what's supporting the cone is the magma. In other words, liquids like that are incompressible. So the idea, the only thing supporting the weight of that entire cone was simply the magma down there in that chamber. Now, as long as it erupts and is replaced, then you're still okay, because you still have the support for the cone. But what would happen if you take that magma and disgorge it all? What you have is a hole in the ground, and there's no longer any support for the cone above. And what's going to happen is the cone is going to collapse down into the remains of what was once the magma chamber, and you're going to form this huge elliptical to circular depression, a collapse structure. That's what a caldera is. So a caldera is a collapse structure following a very, very large eruption that voids much of the magma chamber. Now, typically, they fill with water. That's not uncommon. They fill with water because there's the big basin sitting there. And then every once in a while, they try to come back. So the one I'm thinking about, of course, is Crater Lake. That's what you see there today, Crater Lake. Note, wrong name. It should be called Crater Lake. It should be called Caldera Lake because it's not a crater, it's a caldera. And you see Wizard's Island sitting out there. What Wizard's Island is, it was sort of a last-ditch effort to come back. And it just made a little cone, built up above the water, and there you are. So that would be the difference then between a crater and a caldera. So one is something that every volcano has, a crater, but not every volcano has a caldera. And there's another volcano, a caldera, that I want to talk about. I'm going to hold that one too, because this is going to be a gigantic one. All right, the last features I want to talk about, these are also volcanic features, although we're not talking here about anything to do with magmas or lavas or anything like that, but they're still a volcanic origin because they are created by heat from some kind of a magma mass below. And we're, of course, talking about hydrothermal features. We're talking about things like hot springs, fumaroles, and geysers. Let's think of the hot springs first. We talked about the rift zones. And if you went to New Mexico and took a little trip along the Rio Grande Rift, you'd find a lot of hot springs along. These are waters, groundwater, being heated by the presence of that magma down below, just rises to the surface to produce these hot springs. So those would be of volcanic origin. Now, I make that distinction because someone always asks me about the hot springs and warm springs we have in the east. We have Warm Springs, Virginia. We have Hot Springs, Virginia. And they ask, well, are they of volcanic origin? No, they're not. We don't have any molten rock beneath us anymore. We're an opening system, you see. The Atlantic is an opening system. We haven't had any molten rock under this part of the world for a very, very long time. So what heats the water? Well, there's a thing called a geothermal gradient. The idea is that as you go deeper and deeper into the Earth, about for every 100 feet you go down, the temperature rises roughly 1 degree. So that's just a geothermal gradient. So picture now water seeping into the Earth, in that case over there at Hot Springs and Warm Springs, Virginia, probably along some kind of a fault zone, becoming very deep within the Earth, become heated up, and then, as all hot things do, they rise back to the surface and happen to rise in springs we identify as hot springs or warm springs. Even hot springs isn't really very hot. It's about body temperature. So that has nothing to do with volcanic activity. That's strictly the geothermal gradient. That's also the reason why for the geothermal gradient, that's the reason why the gold mines of Africa have to be air conditioned and why the workers have to wear vests packed with ice because of the geothermal gradient. They're down so deep, you see, that the place is very, very hot. So that would be hot springs. Now, fumaroles. A fumarole, by definition, is a jet of superheated gas. Now, it doesn't say what the gas has to be. It doesn't have to be any particular gas. It's just that most of the time, certainly in my experience in going to volcanic areas, it's steam. So you have these jets of steam coming out of the ground. And now, over the years, these have been harnessed as a result of using this stuff for, we call it geothermal power. For example, to drive a turbine at a power plant, all you need is steam at about 500 degrees centigrade and 150 atmospheres pressure. Well, a lot of these fumaroles generate stuff like that. So all you have to do is tap on one of these natural fumaroles and drive a turbine and make electricity. For example, the biggest natural geothermal power plant in the world is just north of San Francisco at a place called Geysers, California. Shouldn't be called geysers, should be called fumaroles, but I guess it's geysers sounds better than fumaroles, California. Now the geysers, here's an interesting point. You all know what you're thinking now, Old Faithful. What a geyser really is sort of a combination of a hot spring and a fumarole that goes through a cycle. In other words, it starts off at a hot spring, and then it starts getting hotter and hotter, and the hot water starts coming up, blasts the steam, and then settles back down, and it just does that over and over and over again. That's basically a geyser. Now, here's the important thing about it, though. There are only 3 places in the world that have geysers: Yellowstone Park, Iceland, and New Zealand. So these are not very common things. And the one, of course, everybody knows is Old Faithful, which I might add is becoming less faithful all the time. But we'll get around to talk about Old Faithful when we find to talk about, obviously, I will talk about Yellowstone Park, but that's going to be another topic in another lecture. We'll see you then.